Well, REM sleep is really a fascinating state of body and brain. And let me tell you a little bit about what's going on there. Yes, it's rapid eye movement sleep, but it's so much more than that. So, the cerebral cortex is in this desynchronized state, and electroencephalographically, that is high frequency, low amplitude brain waves. Uh, but when we look at the brain with imaging methods, we know that there are some really interesting features of blood flow that suggest that certain parts of the brain actually have increased activity over resting conditions, whereas others have decreased activity. Specifically, those areas that are increased include structures that are in the medial parts of the forebrain, structures associated with the limbic forebrain, such as the anterior cingulate cortex, our medial temporal lobe memory system in the parahippocampal gyrus. Just in front of that, we have the amygdala. So, as we'll see in a different tutorial, these are all structures that are intimately associated with the experience and expression of emotion. And the hyperactivity of these structures during REM sleep very well may be responsible for the emotionality that seems to be present in so many of our dreams. Meanwhile, those parts of our brain that are otherwise involved in executive control functions, such as this dorsal lateral prefrontal cortex, these regions actually show decreased activity relative to the resting state. And perhaps with a decrease in the moderating influence of this executive control network, this might help explain why sometimes the content of our dreams can be socially inappropriate. So, yes, indeed, REM sleep is the phase of sleep where most, but not all, of our dreams occur. I'll have more to say about dreams in just a minute. So, as we cycle through our stages of non-REM sleep and then enter REM sleep, it's not just the brain state that's being modulated, but also the state of the entire body. So, this can be assessed in a variety of means, and here are some data that are fairly typical in terms of what might be gathered during a sleep study if one were to go to a clinic that's specialized in the treatment of sleep disorder. Now, these are somewhat idealized data, so most of us don't have such beautiful looking cycles of non-REM to REM sleep throughout our typical night. But nevertheless, this shows a typical night's sleep where we cycle through non-REM and REM sleep. We tend to spend increasingly more time in REM sleep as our night progresses, and then less time in stage 4 sleep, and eventually even less in stage 3 sleep as we approach waking time, wherever that happens to be for you. Now, during these phases of non-REM and REM sleep, movements of our body's muscles, including those visceral muscles that are necessary to sustain life through sleep, are being modulated. So here what we have is a record of the electrooculogram, which is indicative of when we are moving our eyes. And sure enough, as we enter rapid eye movement sleep, that's where we find an increase in this electrooculogram activity, indicating rapid movements of the eyes during REM sleep. Meanwhile, this is EMG, or electromyographic data, recorded from a limb muscle. And what we see is that, of course, when we're awake, there's a fair amount of activity. And as we're falling asleep, this activity begins to subside. It begins to pick up again as we pass back through our stages of non-REM sleep towards REM. But during REM sleep, and this is especially obvious as we have longer bouts of REM sleep, there seems to be a suppression of muscular activity during REM sleep, and this is really amazing. It in fact is the case. So for most of our large skeletal muscles, there is active suppression of muscle activity during REM sleep. Now, some have suggested that this is adaptive. This is so that we don't act out our dreams with our musculoskeletal system. That may be the case. We don't exactly know how to interpret this phenomenon, but there is some really fascinating neuroscience that explains the inhibition of alpha motor neurons that innervate these large skeletal muscles during REM sleep. I'm wondering if you can hear that. The barred owls in the woods behind me are starting to go crazy over something. I don't know exactly what's going on there, but hopefully they'll calm down. Now notice what's going on in our visceral motor system. So while we are phasing into our deeper states of non-REM sleep, our heart rhythms are subsiding, so are our respirations. But as we begin to cycle towards that paradoxical sleep, that REM sleep, there's an increase in both heart rate and our breathing rhythms. And so again, this is perhaps consistent with activation of the limbic forebrain, consistent with a heightened sense of emotionality. And then also for men, men experience penile erection during REM sleep, and women experience an increase in vaginal lubrication during sleep. Again, perhaps consistent with an increase in activity coming out of the limbic forebrain, which is also highly engaged in various kinds of sexual behaviors as well. So just a couple of other interesting points about REM sleep that are worth making. While sleep is necessary for life, it appears as though REM sleep might not be necessary. As I mentioned earlier, when we were thinking together through some of those opening questions, there are individuals that are taking medications that suppress the experience of REM sleep. That would be a side effect of their medication. And these individuals seem to be getting along quite well. Their lives are not in jeopardy, at least not because of the cessation of REM sleep. Now, it may not be so clear why we have REM sleep, but most of our dreams happen during REM sleep, and so perhaps that's providing us some insight that maybe what's really important about REM sleep is the opportunity to dream. This is an idea that's been with us for some time, and it's regaining traction with some new neurobiological studies that are being done to try to explore the possible benefits of dreaming. So while REM per se is still quite mysterious in its significance biologically speaking, perhaps it's at least providing a space for the experience of dreaming, which we'll turn to in just a moment. So, as Hamlet said in his famous "To be or not to be" soliloquy, to sleep, perchance to dream. So, many of us, like Hamlet, have wondered about dreaming and what it might actually be doing for us. And, of course, many over the last 150 years or so have argued vigorously about this. Certainly, Sigmund Freud had his ideas about the importance of dreams. Freud argued that dreams provided a means for the ego to relax its grip on the id. Now, most of us don't really adhere to these Freudian concepts. We want to replace them with neurobiological concepts, and so we're not quite sure what to do with this one. But there may be a sense in which Freud was ahead of his time, at least anticipating some of the brain mechanisms that reflect a difference between explicit processing in the brain and implicit processing. Well, there's an idea that says that dreams are really an opportunity to rehearse some of the less common behaviors that are not often expressed in the waking state. For example, very intense emotional states, perhaps aggression. So various kinds of behaviors that might be risky and self-destructive if they were to occur during wakefulness might be played out vicariously through dreams. Well, there's another idea. It says that a dream is an opportunity to unlearn, that is, to erase some kind of non-adaptive pattern of neural activity, perhaps stored as a memory. So this could be a very useful mechanism for us to get rid of unwanted memories. Well, there's another thought that seems to be gathering a lot of interest these days, which is exactly contrary to this last one. Rather than dreaming being about unlearning, the prevailing view, I think, among neuroscientists today is that dreaming, in fact, provides an opportunity for synaptic plasticity. That dreaming provides us with opportunity to consolidate memories, to engage mechanisms of synaptic plasticity, and retain the learning of the day. So there are a variety of studies that are showing evidence for this view, from behavioral studies to neurophysiological studies, and it's quite exciting to see this emerge as potentially a neurobiological mechanism that explains the benefit of dream. Now, there's so much yet to be discovered about this. We are far from understanding exactly what's going on here, but it's an intriguing concept that dreaming provides us an opportunity to actually consolidate the learning of the day. Well, there are still some nihilists out there that would say that dreaming is nothing but an epiphenomenon, that perhaps actually REM sleep is important after all. We just don't understand why it's important yet. But dreams per se may just be epiphenomenal. Well, I think the sum of all this is that no one really knows why we dream or even how we dream. But we are developing some concepts that I think maybe are leading us down a fruitful path. So let's see where this goes over the next decade or so, and hopefully we'll have much greater insight into both the nature of dreams as well as the neurobiological mechanisms underlying dreams. Well, it's to some of those mechanisms that we do understand that I want to turn to now. So let's consider some of the neural circuits that are important in governing sleep. So, as should be clear to you by now, sleep involves a series of transitions from one state of body and brain to another. And this reflects a complex interplay among a variety of neurochemical systems that are present in the hypothalamus, in the reticular formation of the brainstem, and these are systems that have widespread projections that can affect circuitry really throughout the central nervous system, even down into the spinal cord. But they are especially focused on modulating the way the thalamus interacts with the cerebral cortex. So I'm going to give you a bit of a detailed run through these mechanisms, and then we'll come back and talk about them in slightly broader brushstrokes. So what I'd like to do is go through this table and lay out for you some of the details about which neurochemical systems are involved in which brain states, and then we'll come back and talk about how they interact with one another. So first, let's consider the maintenance of wakefulness. So wakefulness is a product of the activation of quite a large number of neurochemical systems. Among the most important are the first two listed here in this chart, the cholinergic nuclei that are found near the junction of the pons and the midbrain, and the locus coeruleus. The locus coeruleus is a collection of cells in the dorsal tegmentum of the pons that produce the neurotransmitter norepinephrine. So together, these two, acetylcholine and norepinephrine, very important neurotransmitters in maintaining wakefulness and maintaining vigilance. But in addition to acetylcholine and norepinephrine, we also have other neurotransmitters, the serotonin system, which are derived from the midline raphe nuclei that are found right in the seam of the brainstem, raphe meaning seam. There's an important nucleus in the posterior hypothalamus called the tuberomammillary nucleus. This nucleus produces histamine, and histamine, when it's active, promotes wakefulness. The lateral hypothalamus is home to collections of cells that produce a variety of peptide neurotransmitters. One of them is this peptide called orexin, sometimes called hypocretin. And orexin, when active, promotes wakefulness mainly by stimulating these tuberohypothalamic hypothalamic cells that then release histamine. But orexin has other roles to play in other circuits that project out of this lateral hypothalamus. So these are systems that promote wakefulness. The systems that then promote falling asleep, feeling drowsy, involve basically a decrease in the activity of many of the ones that I've just mentioned. So the functions of acetylcholine, of norepinephrine, of serotonin, they are all decreasing as we are entering the stages of non-REM sleep. So we're going to talk a little bit about the neurochemistry as to what's pushing these systems that were active in the waking state towards decreased activity in non-REM sleep. Well, this leaves us then with a consideration of the neurochemistry of REM sleep. Now, in REM sleep, we have a bit of a hybrid state where the brain is active, the body is in this suppressed, partially paralyzed condition. And this dichotomy between an active brain but an inactive body and yet being asleep implies that there must be some differentiation of neurochemical systems, some of which might be turned on, some of which might be turned off. And indeed, that seems to be the case. The cholinergic nuclei of this junctional region between the pons and the midbrain are active, in fact, in a quite unusual pattern of activity that produces a very discrete type of electrical signature that propagates from the pons into the lateral geniculate nucleus of the thalamus and then into the occipital cortex. These are called ponto-geniculo-occipital waves, or PGO waves. So there's a very distinct pattern of activity that's present in these brainstem cholinergic neurons. Meanwhile, some of the other amine neurotransmitter systems that otherwise might support a more wakeful condition are inactive. This would include our norepinephrine system and then the indolamine system involving the neurotransmitter serotonin. So both serotonin and norepinephrine are depressed at the same time that the cholinergic system is turned on in this very peculiar way. So there are a variety of mechanisms then that are operating, some of which are being pushed up, some of which are being pushed down, that help explain these very peculiar transitions that we have in our state of body and brain. Well, I'll give you a bit of an anatomical view of some of these systems now. So our cholinergic nuclei that are so important in maintaining wakefulness and then are turned on during REM sleep are found here in the rostral pons and in the caudal midbrain. And these neurons have projections that are directed up towards the thalamus. They also have some projections down towards other parts of the reticular formation in the medulla. Our raphe nuclei are found along the midline of the brainstem, from the midbrain all the way down into the medulla. And these raphe nuclei give rise to very long projections that basically extend all over the entire brain and even down into the spinal cord, where they release serotonin. The tuberomammillary nucleus is a very small nucleus in the posterior part of the hypothalamus, and it gives rise to projections that extend throughout the entire central nervous system. And these projections release histamine. And this histamine is an important neurotransmitter in supporting the wakeful, active brain. And as many of you who have seasonal allergies know, if you take an antihistamine, you are very likely to feel drowsy. And it's because you are antagonizing this natural, wakeful, promoting chemical in the brain. And finally, we have this beautiful structure found along the dorsal tegmentum of the pons called the locus ceruleus. And this is the location of the cell bodies that produce norepinephrine. And norepinephrine is right up there with acetylcholine and histamine as being among the important neurotransmitters that support wakefulness. These noradrenergic fibers extend throughout the central nervous system, releasing norepinephrine and modulating our level of arousal, vigilance, and attention.